Let's move now to access methods. So how to access files and which is the minimum unit we can read or write from secondary storage or the disk. So we can go in two ways here. One is sequential access. So the idea is that we start reading a file from the very beginning, and then we have functionality that allows us to take the next, let's say, piece of information in the file. We would say this is called block, or to go back. So it's like scanning a file. This could be a way to access the information in a file, and the operating system can give you functionalities to do this sequential read. But we can also have direct access. So we might want functionality that allows us to read or write at specific offsets in the file so that we can rapidly go where we want instead of just scanning everything. It depends on the type of file. If you have to listen to a song that is in a file, then most likely you're going to scan everything because you have to read the entire file in order. If you are accessing a data file and you only need to take some specific data values and you know how the file is organized, like a matrix maybe, then you can go in a specific offset and read the stuff. Now, independently of which one of the two we use, the operating system reasons in terms of blocks, okay? So whether we read one thing after the other or we access something at a specific position, the minimum unit we can use to interact with the disk is called block, which is a group of or a certain amount of bytes, as you can imagine. So why do we read blocks instead of just bytes? Why don't we go give me the next byte or give me or go to a specific byte? Remember, this is not inside the memory. This is when we actually want to read something from the disk. Well, you remember this, we saw some lectures ago, that whenever you have to read or write something from the disk, the CPU cannot directly communicate with the disk. It needs to go through several cycles because, as we said, the CPU only reaches main memory directly, which means we will have system calls, context switches, we have to move processes in a waiting queue, we need to wait for the input-output of the disk, interrupts, and so on. So you can imagine that pay all this price every time you need a byte and you have to read a very large file doesn't really make sense, right? It's too much of a read. So instead, what we do is that if we read or write something, then we take a chunk of the file, because similar in spirit to the concept of locality, you know that if you need a certain byte, most likely you also need bytes that are around that one. So now the question is, fine, let's use blocks instead of bytes. How big should a block be? If the minimum unit, the block, is all you can read or write, and you choose a very large block, the good thing is that you don't need to read or write a lot of blocks when you have to store or read something. On the other hand, if a block is, let's say, 1 megabyte, and you want only to write a file that takes a couple of bytes, then you're going to waste a big chunk of that block because you can only write blocks. On the other hand, if you use small blocks, you can better utilize the disk because you waste less space, but then you need to read or write or access in general more blocks when you have to do something with a file. And actually, you can see that as always, these trade-offs have result in different behaviors. So in this graph here, you have different block sizes from 1 kilobyte to 1 megabyte, and then you have two lines. The solid one is the disk space, and the dashed one is the data rate. So what are we seeing here? If you look at the data rate, which is the dashed one, you see that the higher the block, the larger the block, the higher the data rate, okay? So basically you can go up to 60 megabyte per second if you have blocks of 1 megabyte. It depends, of course, on what disk you use, its own speed, and so on. But the idea is that this will grow. But on the other hand, if you have small blocks and you need to read a lot of them, then the data rate will decrease because you have to do more context switches and so on. On the other hand, if you look at the disk space, which is the solid one, you see that if you have very small blocks, which means you don't waste blocks when you have to write small amounts of bytes, you can use almost the entire disk to actually store the information you want. But if you start having a lot of, large blocks, then there are higher chances that you will waste space in these blocks and the total disk utilization will go rapidly through towards 0%. Don't get confused here. It's not that, you are utilizing the disk at 100% if you write all the blocks, but you are not really utilizing 100% of the disk because many of these blocks do not really contain, or their content is not completely related to what you're writing, it's just waste space because you have to write a megabyte despite the fact that you actually just need a couple of bytes for that. So trade-offs as always. And one of the complicated things here, we already mentioned this also for memory, is that if you know what is the average size of your file, then you can probably take the best decision to maximize space utilization while having still a good data rate. But you cannot really take such a decision in advance because when you design the file system, you don't know yet what files will be stored. That depends on the user and how he uses the computer and so on and so forth, which of course complicates even more the matter here. Now, this is just a question I just answered. So why is it challenging to choose the right block size? Because you don't know in advance what the user will actually store on the disk.